Hello there and welcome. This is one of many videos aimed at supporting you and helping you with AQA A-level chemistry. There are several other videos available, so please check them out. If there are any videos missing that you think you'd like support with, please do get in touch and let me know, and I'll try and sort some videos out. This video focuses on the rate equation and the 3.1.9 specification point. It will cover briefly some prior knowledge stuff based on the AS specification and possibly GCSE, depending on which specification you followed. Whenever you do revise and you're doing work, I do strongly advise you have a copy of the spec in front of you, because it's very clear on there, like the things that you're expected to know and what you'd be able, what you should be able to do for the exam. So this is focusing on the rate equation. We'll introduce the term order of reaction with respect to reactants and using experimental data to determine the rate equation and calculate the rate constant K with its units. Very, very common exam questions, these. So we're focusing on these specific areas. Right, let's get started. So what's actually meant by the term rate? What is it? Kinetics is the study of the rate of a chemical reaction, and when we say rate, we could measure that in two ways. It's either how fast a reactant is being used up, or it's how fast the product is being formed. So the faster a reactant is being used up, the faster the rate of the chemical reaction, and likewise the faster a product is being produced, the faster the rate of the chemical reaction. Now, units for that would be change in concentration per second. That's a good way of measuring how fast something is being used up or being produced. So units for rate are moles per decimeters cubed per second. Just some reminders of some notation. If you put square brackets around a substance, that means it's the concentration of that substance in moles per decimeters cubed. You see this in AS when you do the equilibrium constant Kc. We use square brackets to show moles per decimeters cubed. We're going to mention initial rates quite a lot through this. The initial rate is the rate at the very beginning of a chemical reaction, because the rate will change during the reaction. It will always be the fastest at the start, and it will go down to zero at the end once the reaction stops, once one of the reactants is used up, the limiting reactant. So we'll use the term initial rates a lot, okay? So one thing you should have done from GCSE is looking at concentration time graphs, and you'll have done that a little bit at AS, so let's start there. Okay, so what we're looking at here is a concentration time graph, and I can see that the concentration is decreasing over time. It's starting at 0.1, it's going all the way down to 0. So that's telling me that this must be the concentration of a reactant since it's being used up. If it was the concentration of a product, we would see it increasing over time. And what we can do here is to calculate the rate, we need to determine the gradient, the slope of that line. Now, because it's a curve, the gradient is changing. The gradient is the greatest at the beginning at 0 seconds, and it's going all the way down to 0 gradient at the end when the reaction's stopped. So the gradient is helping us, or determining the rate of reaction. Now, if I want to determine the rate at time equals 0, so I'm going to time equals 0, what I need to do is draw a tangent at this point. So it must touch the line at time equals 0. I'm drawing a nice straight line. And what I'm going to do is my rise over run, so 0.1 divided by, then my units across the bottom here, there's 30, so that's, well, just about 25 seconds there, okay? So I would determine my rate of reaction is 0.1 divided by 25. That would give me an answer in moles per decimeters cubed per second, okay? And you can quite easily work that out when you calculate it again. If you wanted to do the rate at 40 seconds, I would draw another tangent at 40 seconds, which would have a lesser gradient because the rate's going to be smaller there, and I would determine the gradient again. So I could determine the rate at any given point, okay, and we could be expected to do that in the exam. You've probably done a required practical that required you doing this, and you'll have done that as well. So what is the rate equation? The rate equation is it's a mathematical representation of how concentrations of reactants affect the rate of reaction. So it's a study of the kinetics, but it's a mathematical representation. And the rate equation will always have the form of rate is equal to the rate constant K. Now the rate constant K changes with each reaction. It's not the constant for every single reaction. It's specific to the reaction that we're talking about. So this reaction that I'm going to talk about will be A plus B forming 2 lots of C and 1 D. So that's a general chemical equation. A plus B. In fact, I'm going to put a 2 in front of the A there. So 2A plus B makes 2C plus D. Now the rate equation, rate is only going to be affected by reactants or a catalyst. The rate is not going to be affected by products. So the rate equation will not have any C or D in it because the concentrations of C and D will not have any impact on the rate. Only the concentrations of the reactants and possibly any catalysts. We'll see more of that later. So the rate equation is going to be equal to a rate constant K, and this rate constant K is specific to this reaction that I'm doing here. So the rate equals K multiplied by the concentration of A to the power of X multiplied by the concentration of B to the power of Y. Now notice these X and Y's, they don't appear anywhere in the chemical equation, and that's correct. Sometimes people wrongly think that they come from the coefficients. For example, some people believe that X would be 2 because it's the coefficient there in the chemical equation and Y would be 1. That's incorrect because I know we do use these coefficients when we do the equilibrium constants, but we definitely don't use them when we do the rate constants. So this X and Y bear no resemblance of the chemical equation itself. X is known as the order with respect to A, and Y is the order with respect to B. Now the order is limited to either 0, 1 or 2, so first, second. So the orders have to be 0, first or second. So X and Y have to be 0, 1 or 2. Now what does that even mean? Well, if it's 0 order, we've got the concentration to the power of 0. That just means in maths, anything to the power of 0 is 1. So if we're saying that it's 0 order, what we're actually saying is the concentration does not have any effect on the rate. So for example, if X was 0, we're basically saying that the concentration of A doesn't affect the rate of reaction because it's 0 order. Likewise, if Y was 0, we're saying that the concentration of B has no effect on the rate of reaction. If it's first order, then it's directly proportional. If you double A, you would double the rate. If you halved A, you would halve the rate. Likewise, if Y was 1, it would be first order with respect to B. If you trebled the rate of B, you'd treble the rate. If you quartered the concentration of B, you'd quarter the rate. So that's if it was first order. If it's second order, you can kind of see where we're going with this. If it's second order, so let's just say it's second order. If you doubled the concentration, the rate would go up by 4 because it would be 2 squared. If you halved the concentration, then you would quarter the rate. So it's a mathematical representation where the orders are 0, 1 or 2. And they're basically showing or telling you the degree at which any change in concentration, how that impacts on the rate. So 0 order means it doesn't affect the rate. First order means it's directly proportional. Second order means that it's proportional to the change in concentration squared. Okay, so it is just a mathematical representation. So how do we determine the rate equation from experimental data? So let's have a look. So we've got a reaction here. Again, it's a very general equation. 2A plus B goes to C plus 3D. And we're given some experimental data here. There's been 3 experiments carried out, 1, 2, 3. And what they've done is they've changed the concentrations of the reactants A or B, or in some cases A and B, and they've measured the initial rate. Right, so before I even start trying to work this out, I know that the rate equation will have the form of rate equals K, and because there's 2 reactants here, it's going to be A to the power of X, concentration of B to the power of Y. These square brackets are essential, by the way. We must have square brackets because that's telling us its concentration in moles per decimeters cubed. So I know the rate equation is going to have some resemblance to what I've just written there. Rate equals K multiplied by concentration of A to the power of X and concentration of B to the power of Y. There's no mention of a catalyst there, so I'm not showing any catalyst in my rate equation. Right, so here's our experimental data here. So I know that the rate equation will take the form of rate equals K multiplied by the concentration of A to the power of X multiplied by the concentration of B to the power of Y. So what I'm going to do is I'm going to compare two experiments where the concentration of one of the reactants doesn't change. So if I look at experiments 1 and 2, so if I'm comparing experiment 1 to 2, I can see that the concentration of B doesn't change, multiplying by 1. However, the concentration of A is actually doubling, multiplying by 2. And what's happening to the initial rate during all this? Nothing. It's staying exactly the same, multiplying by 1. So what I'm going to do is come down and I'm going to say, well, the rate is just multiplying by 1. Concentration of A is multiplying by 2, and it's 2 to the X. Not sure what X is just yet. Concentration of B multiplying by 1, and it's 1 to the Y. Now, 1 to the Y is just 1. Doesn't matter what the value for Y is, whether Y is 0, 1 or 2, it will always be 1. So 1 to a 0 is 1, 1 to the 1 is 1, and 1 to the 2 is also 1. So I can remove this actually, because it's just going to be 1. So I've now got 1 is equal to 2 to the X. I now need to determine the value for X. So X is either 0, 1 or 2. 2 to the 0 is 1. That's correct. If it was 2 to the 1 it would be 2, or 2 to the 2 would be 4. So what I've just determined here is in fact X is equal to 0. Okay, so I've determined that X is equal to 0. I can go back to my rate equation, get rid of the X. I can say it's 0. But in fact, anything to the power of 0 is just 1. So I can actually, when it's 0 order, so I've just determined that it's 0 order with respect to A. So it's 0 order with respect to A. So I can actually, when it's 0 order, I don't even need it in my rate equation because it's not having any impact whatsoever on the rate of reaction. It's 0 order. So I've determined that X was equal to 0. So it was 0 order. I've removed it from my rate equation. So what do I need to do next? I'm going to now compare two further experiments, this time where the concentration of B changes. Okay, I've got two choices. I could compare experiments 1 and 3, or I could compare experiments 2 and 3. It does not matter. I'm going to compare experiments 1 and 3. A is multiplying by 1, but we actually already know that that's completely irrelevant now because A is 0 order, so it doesn't matter what I do to A, it's not affecting the rate. Comparing experiments 1 and 3, concentration of B is multiplying by 3, it's trebling. And what's happening to the initial rate? Well, at first glance it might appear that the rate's going down, 2.00 to 1.8. However, be careful, look, standard form. So this is actually a bigger number. 1.8 times 10 to the minus 3 is a bigger number than 2 times 10 to the minus 4. Okay, it's actually 9 times bigger. If in doubt, you just take 1.8 times 10 to the minus 3, divide by 2.00 times 10 to the minus 4, you will get 9. So it's multiplying by 9. So what have I just worked out? I've worked out that the rate is multiplying by 9. The concentration of B is multiplying by 3, and it's 3 to the Y, where Y is equal to 0, 1, or 2. If Y was 0, then that would be 1, but it's not, it's 9. 3 to the power of 1 would be 3, it's not, it's 9. 3 to the power of 2 would be 9. Okay, so we've just determined that Y is equal to 2. So we've just determined that the order with respect to B is 2. So it's second order with respect to B. So my rate equation is rate is equal to K multiplied by the concentration of B squared. So that's my rate equation. It's second order with respect to B, 0 order with respect to A, and therefore the overall order is 2, because 2 plus 0 is 2. Okay, now those numbers were quite nice as a whole, but so we've determined the rate equation using that experimental data as rate is equal to the rate constant K multiplied by the concentration of b squared, because it was second order with respect to b. Okay, so now we've determined the rate equation, we can actually find a value for the rate constant, because as I've said, the rate constant is specific to this reaction. Okay, the rate constant is specific to this reaction and at specific temperatures. As we can see, and we already know that the temperature affects the rate of reaction. It's one of the first things we do way back in GCSE and even earlier, that if we increase the temperature, the rate of reaction increases. Now, temperature doesn't appear in the rate equation, therefore the temperature impacts on the rate constant K. So if you increase the temperature, the rate constant increases. That's why these experiments must all be carried out at the same temperature. So that's our rate constant K, and it's specific and it changes at different temperatures and for different reactions. Now, we can rearrange this to get K is equal to the rate divided by concentration of B squared. So I'm just rearranging this equation. And then what I do is I can select any experiment. It doesn't matter whether it's 1, 2 or 3. I'm just going to pick experiment 1 because it's up the top. So rate constant is equal to the rate, which in this case, experiment 1 is 2.00 times 10 to the minus 4 divided by the concentration of B squared, which is 1 squared. So my rate constant here is 2.00 times 10 to the minus 4. Now I need to deduce the units, and this is normally the scary part for a lot of people that aren't comfortable with the maths or with units. Now I'm going to use the same formula. K is equal to rate divided by the concentration of B squared, and I'm going to put the units in. Now the units for rate is moles per decimeter cubed per second. Okay, and the concentration of B is moles per decimeter cubed, but that's squared. Okay, now what we've got here, we'll always have this on the top expression, the moles per decimeters cubed, and we'll have some moles per decimeter cubed on the bottom, but that can change because the rate equation will be different for different reactions. So easiest way to do this is to put brackets around the moles per decimeters cubed, that's 1, and then however many we've got along the bottom, the law of indices, we've got a 2 here. So moles per decimeters cubed to the power of 1 on the top and moles per decimeters cubed to the power of 2 on the bottom. What we need to do to bring this bottom bracket up to the top, we need to do 1 take away 2. That's the law of indices. When you divide, you take them away. So we're going to end up with, on the top row, moles per decimeters cubed to the minus 1, because we did 1 minus 2. The seconds to the minus 1 has just remained the same. Now I'm going to multiply the brackets out. Moles to the power of 1. So moles to the power of 1 times by minus 1, because when you multiply indices, we multiply them. So 1 to the minus 1. So that's going to be mol minus 1. Then the minus 3 minus 1. That becomes dm plus 3. So I've deduced my units as mol minus 1 dm cubed seconds minus 1. Okay. Now you will get better at practicing these units because it is often the biggest stumbling block for a lot of people. So my advice there is the more you do, it does become very logical, and the further examples that we're going to look at next, I'll go through them as well, and I'll use that same method, and hopefully you'll pick that up. Right, so what's going to happen now is there's a different reaction taking place. There's some experimental data there. I want you to pause the video now. You're going to pause the video and you're going to try and determine the rate equation here. You're going to come up with a rate equation, so come up with a general expression. You can see what your reactants are there, so that the products won't be in the rate equation. Come up with your own general expression for the rate equation. Then you're going to use the experimental data to determine the orders. Okay. Once you've done that, try and find a value for the rate constant K, so the numerical value for it, and then determine the units for the rate constant. This should probably take you anywhere between 5 and 10 minutes, depending on how confident you feel right now. So pause it, have a go, and when you're ready, press play, and you'll see me go through this on the next slide. Okay, hopefully you've had a good go at this. Now, what I'm going to start with is I know that the rate equation will take the general form of rate is equal to K multiplied by the concentration of NO, because that's one of our reactants. I don't know what this X is, but to the power of X, and that's the order with respect to NO, multiplied by the concentration of H2 to the power of Y. And again, I don't know what Y is. It's either 0, 1 or 2. Right, so what I do now is I pick two experiments where the concentration of one of the reactants is not changing. I can see that here, comparing experiments 1 and 2, my concentration of H2 is remaining the same. My concentration of NO is doubling. What's happening here to the initial rate? Again, if the numbers aren't that nice, you don't like them. 3.76 divided by 1.88, that tells us what's happening. It's in fact increasing, it's doubling. Okay, so what have I just found out? I found out that the rate will double as the concentration of N doubles and the concentration of H2 remains the same. Now, because this is remaining the same, it's a 1, I can remove that from this expression because 1 to the power of anything is just 1. That's why I compared experiments 1 and 2, because H2 was remaining the same. That's the whole point. So I can remove it at this point. Now, 2 equals 2 to the x. Therefore, x is equal to 1, because x has to be 0, 1 or 2. If x was 0, we'd end up with 1. If x is 1, we're ending up with 2. If x was 2, we'd end up with 4. But we need to get the answer of 2 because the rate is doubling. So we now know that it's first order with respect to NO. So I can put a 1. And in fact, when it's to the power of 1, you don't bother putting that 1. So the rate equation, I know that x was equal to 1. Right, now what I need to do is compare two further experiments, this time where the concentration of NO remains, the concentration of NO changes. Now, it is difficult here actually because the where the concentration of H2 changes, ideally the concentration of NO wouldn't change, but that's not possible here. The concentration of NO is changing in all three experiments, and that makes it an extra level of difficulty. So I need to compare two experiments where the concentration of H2 changes. The concentration of H2 changes in experiments 1 to 3 and 2 to 3. Makes no difference whatsoever which two I compare. I'm going to compare experiments 1 and 3. So what's happening to this? What's happening to this? And what's happening to the rate? Now the numbers aren't that nice here. So what I'm going to do, I'm going to take my calculator, 0.75 divided by 0.5, and that tells me what we're doing. Okay, so literally take your calculator, 0.75 divided by 0.5 equals 1.5. Okay, so I know that this is multiplying by 1.5. I'll do the same over here. 0.144 divided by 0.12. What does that equal? Take my calculator, 0.144 divided by 0.12 equals, and that is 1.2. So this is multiplying by 1.2. Numbers really aren't very nice here. What's happening to the initial rate? Well, 5.08 times 10 to the minus 4 divided by 1.88 times 10 to the minus 4. And that is multiplying by, get my calculator, 5.08 divided by 1.88, and I've got 2.7. Multiplying by 2.7. So really not very nice numbers here. So let's just follow the same logical pattern though. The rate is going up by 2.7. The concentration of NO is going up by 1.2. And I know it's 1.2 to the power of 1 because we determined it was first order. And then it's multiplying by the concentration of H2, which is 1.5 to the power of something. Right, how can I tell you this expression? 2.7 divided by 1.2. I'm going to take this 1.2 down to this side. Equals 1.5 to the y. Okay, so 2.7 divided by 1.2 is equal to 2.25. Okay, I'm getting closer. I know that y has to be 0, 1 or 2. Now it's not 0 because if y was 0, it would just equal 1, and it doesn't equal 1, it equals 2.25. Okay, now I take 1.5 to the power of 1. Well, 1.5 to the power of 1 would equal 1.5, but it's not, it's 2.25. So hopefully if I take 1.5 and I square it, I get 2.25. Excellent. So it's now, I've determined that y is 2. It's second order with respect to h2. So it's now second order with respect to h2. So that's my rate equation. Okay, that's the rate equation there. Right, so what we need to do now, we've determined our rate equation, which was rate was equal to k. It was first order with respect to NO, and it was second order with respect to H2. So what we need to do now is determine a value for the rate constant. Now, rearranging this, we get K is equal to rate divided by concentration of NO multiplied by the concentration of H2 squared. So numerical value, let's just pick any experiment. I'm going to go for experiment 1 again, it's right at the top. The rate is equal to 1.88 times 10 to the minus 4. Concentration of NO is 0.120 multiplied by 0.5 squared. Make sure I have that in brackets on the bottom there. Okay, take my calculator. 1.88 times 10 to the minus 4 divided by 0.12 multiplied by 0.5 squared equals, and I get a value of 6.27 times 10 to the minus 3. So that's my numerical value. I now need to determine the units. Okay, so I'm going to change the colour of the pen so you can see this a bit more clearly, because this is the bit that people tend to not like. It's rate divided by. Now, I'm going to make it a bit more straightforward because I've got concentration of NO, concentration of H2 squared. So what I'm going to do is this represents concentration and this represents concentration in moles per decimeters cubed. So we've got moles per decimeters cubed multiplied by moles per decimeters cubed, but this is squared, so it's times moles per decimeters cubed. So what we've actually got on the bottom is moles per decimeters cubed 3 times, because we've got 2 from here and 1 from here. Okay, so we've got moles per decimeters cubed to the power of 3 on the bottom, and on the top we've got moles per decimeters cubed per second. So we've got 1 mole per decimeters cubed on the top. We'll always have this on the top. It will always be rate on the top. So now what I can do is 1 take away 3. 1 take away 3 is minus 2. So my units are moles per decimeters cubed to the minus 2. Seconds to the minus 1. Now, multiply this brackets out. Mole to the 1 times minus 2, so that becomes mole minus 2, because 1 times minus 2 equals minus 2. Then dm minus 6 times minus 2 is plus 6. So minus 3 times minus 2 is plus 6. So my units are mole minus 2 dm6 s minus 1. Okay, right. Time for you to have another go. Okay, so it's a little bit trickier again. We get a little bit more difficult as we go along. So you're going to, again, same as last time. There's an extra level here. I'm going to give you a bit of a hint. This one contains a catalyst. Okay, and since the catalyst can affect the rate of reaction, then you do need to include the catalyst in your rate equation. So your rate equation can include a catalyst if there's one present. This includes a catalyst, of which in this case is H+, so your rate equation does need to include the concentration of the catalyst in it. Okay, so have a go at this one. It's a bit more difficult, and when you're ready, move on to the, well, pause it, have a go. When you're ready, move on. Okay, and we'll go through it in the next slide. Okay then, so we know the rate equation is going to have the form of rate is equal to K multiplied by the concentration of I2 to the power of something multiplied by the concentration of CH2 COCH3 to the power of something. And because we have a catalyst in this, the catalyst can be in the rate equation because catalyst will affect the rate of reaction. Okay, so the rate equation, we've got three things here. We've got the two reactants and the catalyst. So I need to find two experiments where only one of the concentrations is changing. So in other words, two of those three must remain the same. So it might take you a little while to have a look. It's not always going to be experiments 1 and 2. So let's have a look. If you look through there, experiments, there we go. Experiments 1 and 3, that's remaining the same, and that's remaining the same. So if I'm comparing experiments 1 and 3 here, concentration of H+ is doubling. Okay. What's happening to the rate? Well, again, be super careful because it looks like it's going down, but it can't be because that's doubling. It's, well, yeah, it's also doubling. So what I've just determined is the rate will double if the concentration of the catalyst doubles. So actually, I can just say that it's first order. So you get quicker at these. You see, I'm seeing there, without even doing all the little working out, I can see that comparing experiments 1 and 3, the concentration of I2 remains the same, the concentration of CH2COCH3 remains the same, the concentration of H+ doubles, and that causes the rate to double. So it's now first order with respect to H+. So I know that Z was equal to 1, and again, I don't need to put the 1, it's just first order. There we go. Right, so now what I need to do is I need to find two experiments where the concentration of either I2 stays the same or the CH2COCH3 stays the same. Okay, so one of them changes. Let's have a look. Now, there we go. I'm going to compare experiments 2 and 4 because this is remaining the same. Now what's happened to this one? Well, this is halving. So it's actually, if you're not sure, you can take 0.02, divide it by 0.04, and this is in fact multiplying by a half. Okay, it's multiplying by a half. Try and stick to multiplying rather than dividing. I know it's tempting to say dividing by 2, but try and stick to multiplying. It makes it much easier to work out. What's happening to this? Well, again, take your calculator out, and this is doubling. It's going up by 2. What's happening to the H+? Well, this is doubling. Okay, so it feels complicated now, but let's just stick to our plan. The rate is going up by 2. The concentration of I2 is going up by a half. It's a half to the x. The concentration of this, the CH2, CH3, remains the same. The concentration of H+ is doubling, and we know it's first order. We can remove the 1 to the y because the 1 to the y is just 1. 1 to the power of anything is 1. So what we've got now is 2 is equal to a half to the power of x times by 2 to the 1. 2 to the 1 is 2. So I'm going to simplify this down a little bit. I'm going to say that a half to the power of x multiplied by 2 is equal to 2. So 2 divided by 2 is equal to a half to the x. 2 divided by 2 is 1. So we now know that x is 0. We're basically now saying that the concentration of I2 has no effect on the rate whatsoever. We know that x has to be equal to 0, 1 or 2. Anything to the power of 0 is 1. If this was to the power of 1, it would be half. If it was to the power of 2, it would be a quarter. Okay, so we've now determined that x is equal to 0. So it's 0 order with respect to x, which means I can remove I2 from that equation. Right, we're getting somewhere near now. We now need to determine the order with respect to CH2, C, or CH3. So let's pick 2 experiments now. I'll change colour to a green. Let's find where the concentration of the CH2, CO, CH3 changes. Now, just to compare different experiments, I'm going to compare experiments 3 to 4. 3 to 4, 3 to 4. Notice how I'm completely ignoring this, because even though it's staying the same, I've got confidence now, because I've removed it from the equation, that the concentration of I2 has no effect whatsoever on the rate. Right, so what's happening to the rate? 1 is going from 1.8 to 2.4, so I'm going to go 2.4 divided by 1.8. That's 1 1/3, so this is 1.33. That's 1 1/3. What's happening here? Well, this is just by 1. What's happening to this? So 8 divided by 6 is 1 1/3. So what I'm just saying here is that the rate is increasing by 1.334. The concentration of this is increasing by 1.334. That's to the power of y, and that's 1 to the 1, because this is first order and that's remaining the same. So 1 to the 1 is just 1. Remove that. 1.334 equals 1.334 to the power of what? Well, that means that y is 1. So it's first order with respect to CH2, CO, CH3. So I can change the y. That's a 1. Again, we don't bother writing the 1. So that took some working out, but my rate equation was first order with respect to CH2, CO, CH3, and first order with respect to H+. So there's my rate equation there. We've still got to now determine a value for the rate constant, and we've got to determine units for the rate constant. So let's have a look. We've just worked out that the rate equation is equal to K multiplied by the concentration of CH2, CO, CH3. It was first order, and it was first order with respect to H+. So we now know we can rearrange that to get K equal rate divided by concentration of CH2, CO, CH3, concentration of H+. So we can take some numbers. I'm just going to use experiment 1. The rate is 9.0 times 10 minus 5 divided by 6 times by 0.5. So I'm just literally taking the numbers from the table, putting them into the rate equation. What does that equal? Well, let me work it out. 9 times 10 to the minus 5 divided by 6 times 0.5 equals 1, 2, 3, 4 minus 5. I need units though. Okay, we need some units. I'll change my colour to work those out. So let's get some units for this. Units. Well, K is equal to the rate divided by concentration times concentration. So I'm going to, on the bottom, I've got concentration and concentration in terms of units. So my units then, rate is measured in moles per decimeters cubed per second. Concentration is measured in moles per decimeters cubed, moles per decimeters cubed. We're multiplying them together, so it's in fact moles per decimeters cubed squared. Okay, Now, what I've been doing so far in previous examples is I've been putting square brackets around that and saying it's to the power of 1 because it makes it easier to put a 1 take away 2 when I'm taking the bottom up to the top, and that leaves me with mol dm minus 3. 1 take away 2 is minus 1, so that leaves me with this, but I need to multiply it out. 1 times by minus 1 is minus 1, so it's mol minus 1. Then minus 3 times minus 1 is plus 3. So my units are mol minus 1 dm cubed seconds minus 1. Okay, so that was quite a difficult example, that one. My advice now is to go away and do as many practice questions as you can, and the more you do, the more straightforward these become. Good luck. Hope you found that useful. Now let's look at a couple of exam questions. What I suggest you do is pause the video now and have a go at this yourself before I go through it. So pause the video now and have a go. Okay, so what are we working with here? We've been given an unfamiliar equation, a reaction there with bromate ions and bromide ions in acidic conditions. And then they're telling us that a series of experiments have been carried out and they've deduced the rate equation. So they've actually given us the rate equation here. Quite often we're asked to deduce that ourselves, but we've been given it here. Use the data from experiment 1 to calculate a value for the rate constant K at this temperature and give its units. Okay, right, well, we know the rate equation is rate is equal to K, concentration of bromate, concentration of bromide, concentration of H plus squared. So we're going to rearrange this to get K equal. K is equal to rate over concentration of bromate multiplied by concentration of bromide multiplied by the concentration of H plus squared. So we're going to take our numbers from experiment 1, put them into our calculator, and we end up with... Okay, now it says give your answer the appropriate number of significant figures. Quite often students miss this out. Now the appropriate number is the minimum number of significant figures used in the question, in which case they're all 2 significant figures anyway. So I must give my answer to 2 significant figures. This comes out to 2 significant figures as 13. So my value for K is 13. That's going to give me 2 marks. I'm going to get 1 mark for the expression, 1 mark for the correct answer. I need my 3rd mark for my units now though. Now units. Units for rate are moles per decimeter cubed per second. Divided by, now this is concentration, concentration, concentration squared. So on the bottom we've got concentration 1, 2, 3, 4. So concentration to the power of 4. 1 take away 4 is minus 3. So we end up with mol dm minus 3 to the minus 3 seconds to the minus 1. Multiply this out. 1 times minus 3 is minus 3. Minus 3 times minus 3 is plus 9. So my units come out at mol minus 3 dm9 s minus 1. Okay. Part B, complete table 1. There's a couple of ways you could approach this actually. It wants us to calculate an initial rate for this. Now we could just use the rate equation and rearrange it. That's probably the easiest thing to do, especially now you've got the rate constant there. So we could just rearrange it, and again you could use it to calculate the rate, initial rate for this one, because you've got your values. So this is just a case of put them into your calculator and getting the correct calculation. So I'll put the answers in for you. You can check where these numbers come from. 0.15 there. Again, we work into 2 significant figures. Looking at the mark scheme, it will allow 0.27 here. Obviously it depends on the level of precision that you're working with, and then we'll also accept 0.46 on this one. Okay, so a different question now. I suggest you pause the video again and have a go at this yourself, and then unpause it when you're ready to hear the answer and go through it. Okay, so this question then, we're told that it's reaction between A and B at constant temperature. Constant temperature means the rate constant will be constant. We're looking then, so we know the rate equation is going to take the form of rate is equal to K, which is the rate constant, multiplied by the concentration of A to the power of X, that's the order with respect to A, multiplied by the concentration of B to the power of Y, and Y is the order with respect to B. Okay, so now what we do is we consider a couple of experiments where the concentration of one of the reactants doesn't change. When I'm looking here, I can see that in experiments 1 and 2, the concentration of B doesn't change. So the first thing I'm going to do is I'm going to consider experiment 1 and 2. And I would write this as part of my answer so the examiner can see what I'm doing. And I can see that the concentration of B doesn't change. So 1 to the Y. Concentration of A is tripling, so it's 3 to the X. And the rate, be careful, it appears to be decreasing, but look at the standard form, it's actually increasing. So 1.89 times 10 to the minus 3 divided by 2.1 times 10 to the minus 4 comes out at 9. So my rate equation is 9 is equal to 3 to the X, 1 to the Y. 1 to the Y is just 1. So 9 is 3 to the X, X equals 2. So it's second order with respect to A. Okay, now what I need to do is I need to consider two different experiments this time, where the concentration of B will change. Now let's consider experiment 2 to 3, 2 to 3, and 2 to 3. So this time I'm consider experiment 2 and 3. The concentration of A is doubling, concentration of B half, and the rate is doubling. So I know that it's going to be 2 is equal to A, which is doubling, so it's 2 squared multiplied by a half to the Y. Simplify this out, 2 squared becomes 4, and I'll drop it down to the other side, so 2 over 4, that's a half. So half is equal to a half to the Y, therefore Y is 1. So it's first order with respect to B. First order. And again, I don't need to put that one in there. So my rate equation now is rate is equal to K, concentration of A squared, concentration of B. Okay, now it's a different rate equation now, so they're giving us a different set of experiments 4 and 5. This time it's a different reaction, it's C and D. So it's C and D. They're giving us the rate equation, look, second order with respect to C, first order with respect to D. So this is very similar to the question that we've just done. So if you follow the same method, we rearrange the rate equation to get K equals rate over concentration of C squared, concentration of D. You can pick experiment 4 because you've got all the data you need there, and you will find that your value comes out at 57. Okay, value comes out 57, and your units will come out as moles minus 2 dm6 seconds to the minus 1. And once you've got that rate equation, you can then use it to calculate your rate for experiment 5, which comes out at 5.4 comes out at 3.99 times 10 to the minus 3. There we go. Okay, so the final 3 marks to this question then. Again, I suggest you pause the video, have a go at it yourself, and then when you're ready, unpause, and we'll have a look at the answer. Okay, so the rate equation for a reaction is rate is equal to K multiplied by the concentration of E. So what that now tells me is that it's first order with respect to E. That's what that's telling me. So the question is, explain qualitatively why doubling. So qualitatively means using words, not numbers. So explain qualitatively why doubling the temperature has a much greater effect on the rate of the reaction than doubling the concentration of E. Well, I'm going to start by saying that we know that if we double the concentration of E, I know that the rate will also double. So doubling the concentration of A, the rate will double. However, doubling the temperature will more than double the rate. And in another video, you will see rate graphs and Arrhenius equation, but the temperature, if you double the temperature, you more than double. Okay, so it's not direct proportion. If you double temperature, you more than double the rate. Okay, so doubling the temperature more than doubles the rate, and this is because that far more particles now have the activation energy or higher. Okay, if you remember your work on AS chemistry as well, when you looked at the Maxwell-Boltzmann distribution. So we can say that doubling the temperature will more than double the rate. Many more particles have the activation energy or higher, which gives you more successful collisions. Doubling the concentration will only double the rate. Hopefully you found this video useful. If you have, great, let me know. If there's anything that you think's missing, if there's any other videos you're looking for, let me know if you can't find them. But please look out for all the other videos, and good luck.